We've just completed synthetic division. We've ran a quiz today that probably challenged your skills there a little bit, and we want to extend our work with polynomials into the factor and remainder theorem. Something that you've already seen is that synthetic division by the factor and substituting into the polynomial with the root actually generates the same results. Let's take a look at setting up the synthetic division and plugging in and just verifying that a minute. I've ran substituting in -1. -1 from our last lesson got the name of root or 0 or x-intercept. And really those words are used interchangeably. The numbers that we're using in that substitution spots are actually possible roots or possible zeros or possible x-intercepts. -1 is not an x-intercept, it's not a root, it's not a 0 because it doesn't generate 0. When I plug -1 into the polynomial statement, I actually get -7. And I should expect that same remainder when I do long division. When I do long division, I actually get the same value, and that's going to lead us to this factor and remainder theorem, a very powerful theorem in working with polynomials. You can try that long division with the other statement that was above, but when a polynomial is divided by a divisor, the remainder is equal to the substitution of the potential roots into the equation. So when I divided by x plus 1, I subbed in -1 into the polynomial, and I actually generated the same statement. So here is the remainder theorem. The remainder theorem, when a polynomial is divided by a binomial, the remainder obtained is equal to the value of the polynomial when x equals a. So that's what we've already been doing a few times. You're going to see that developed over the course of the next few examples. So I'm not going to synthetically divide. I'm actually going to take another shortcut, and that is plug in the potential root, 0, or x-intercept into my polynomial. So set it equal to 0, x equals -1. I'm going to plug -1 into the polynomial. So 6 times -1 cubed minus 4 times -1 squared plus 8 times -1 plus 6 is equal to -6 minus 4 minus 8 plus 6. So I generate a -12. That means x plus 1 is not a factor of this polynomial. It will generate a remainder when I divide by x plus 1. This is my remainder, r. When I plug in 2x minus 1, I get kind of a yuckier number. Remember, you've got to set the factor equal to 0 and solve for x. X equals a half. Now I have to plug a half in. I'll write that out. So plugging in my half, I have a half cubed, a half squared, 8 times a half, and then some coefficients that have to come in front. So I've got 6/8 minus 1 plus 8 divided by 2 is 4 plus 6, and I'm going to convert that into a fraction. So I could recognize that number as 9.75 or 39/4. Because it's not 0, this is going to be a remainder. So again, I'm not going to use synthetic division anymore. I'm going to plug and play on my potential factors. X minus 3 is equal to 0. X equals 3. That's going to be my substitution in. Now it says that the remainder was 131. So 2 times 3 to the power 4 minus 3 to the power 3 minus a times 3 plus 8 is 131. Got a little bit of processing to do. So 3 to the 4 was 81, and then when I hit it with a 2, I get 162. 162 minus 27 minus 3a plus 8 is equal to 131. I'm going to work on collecting my like terms. So after collecting my like terms to be 143, I actually get to present a value for A by subtracting 143 from both sides. That gives me minus 12, and then dividing by minus 3. So we have a very similar example to today's quiz question. The numbers are a little bit bigger, but let's set up those equations. So I've worked on collecting my like terms. Negative 27D and negative 9C are still hanging out, but on the left-hand side I have plus 139. The 139 moves over to the other side through subtraction, and I actually see that I can reduce my numbers. These numbers are all multiples of 9. So I'm going to hopefully make my life a little bit easier a little bit later on. So this is negative 3D minus 1C is equal to minus 20. So I've tried to reduce my writing a little bit. I get to plug in a 2. So 2 to the 4 times 2 to the cube times D, 2 to the square times C, 2 times 5 is 10, and then a minus 8 is equal to 74. So working on collecting my like terms, 2 to the 4 is 16 times 2 is 32. Getting added to 10 and then 8 subtracted, that's 34. The 34 moved to the left-hand side through subtraction. And like my previous example in red, I see that I could divide all my terms by 4. And hopefully that makes my next step a little bit easier. 10 equals 2D minus 1C. And now by the method of either substitution or elimination, I'm going to solve for one of the letters. I see that because my C's have the same coefficient and the same sign, that I'm going to subtract them. So I'm going to take negative 3D minus 1C equals minus 20, and I'm going to subtract 2D minus 1C equals 10. So now we have a long division-like application. Negative 3 minus 2 is minus 5D. Negative 1C minus 1C is canceled. Negative 20 minus 10 is negative 30. And I get to come up with a D value of 6. Now I can go back and figure out what A is, or what C is, pardon me, because now I know what D is. And it doesn't matter which one you go into. I'm going to go into the green. And plugging into the green statement, my value for D, 2 times 6 is 12, minus 1C is equal to 10. Subtract 12 to both sides, gives me my C value and my D value. Well, if this has been the remainder theorem, the factor theorem is hopefully a little clearer. Let's turn the page. Again, feel free to try out synthetic division or long division, but the factor theorem says that x minus a is a factor of the polynomial if and only if, when I plug in the potential root, 0, or x-intercept, I actually generate a 0. Then I get to use those words interchangeably. 0, root, x-intercept. So my question is x minus 4 a factor? Well, if x minus 4 is a factor, then I get to plug in x equals 4 and see what happens. 4 squared plus 2 times 4 minus 24. 4 squared is 16 plus 8 minus 24 is equal to 0. Because of that 0, x minus 4 is a factor. We've been doing a lot of changing factors into roots. Now we have to go in reverse. If I had plugged in 3, that meant that the factor was x minus 3. If I had plugged in minus 2/3, it actually means that my factor was x plus 2 over 3. But I want to generate an integral coefficient. That means that all the values have to be whole numbers. So I'm going to take this and multiply by 3. So that 3x plus 2 is also a potential factor written in integral coefficients. So instead of doing 2 divisions, I get to do 2 substitutions. Which of the following is a factor? Solve for 0. X plus 2 equals 0. X equals minus 2, plug in. 4 times minus 2 cubed minus 16 times minus 2 squared minus 2 plus 4. So after plugging in minus 2, I generated minus 90, which is horrible. That's not 0. So x plus 2 is not a factor. Now I get to plug in the potential root, which is x equals a half. Plug and play that. I see lots of canceling happening for my statement here. 4 over 8 as the first term is a half, which cancels off with my negative half. 16 over 4, which is a negative first, cancels off with my plus 4, so that's a 0. Now, what's the big deal of working with the factor and remainder theorem? I can find a factor and then proceed with synthetic division or division to find the rest of the factors. So that's what we're going to do here. Show that x equals 1 is the roots of the equation. And then find the other roots. So first I have to use the factor theorem, and then I'm going to synthetically divide. So that's a true statement, and now I have to synthetically divide 1 as my root into the original dividend. So in my synthetic division, I came up with the coefficients 1, minus 8, 12, and a remainder of 0. My divisor was x minus 1, so this is my divisor statement. This is my quotient statement, and my quotient statement can be factored into x minus 6 times x minus 2. And because of those other 2 factors, I have 2 other roots, and those roots are x equals 6 and x equals 2. Awesome. That's it for the factor and remainder theorem. Hopefully you get the lesson done today in class.